Hi viewers, welcome. In this video we will see about source free RC circuit in first order circuits. First order circuit is the one which will provide the first order differential equation, and in this chapter we will see the natural response of this circuit and what is time constant, how the time constant affecting the discharging of the capacitor, and whatever the amount of energy dissipated by the capacitor is dissipated by the resistor or not, we will prove it. For this, the circuit is consisting of two elements, that is capacitor and resistor, and capacitor initially fully charged to its maximum value and then connected in this circuit. And if you are assuming that this is the junction, as we know that it is a source free circuit, so the incoming current to this junction is equal to 0, that is incoming current to this node is 0 and outgoing currents are IC and IR. So we can write, as per KCL, we can write IC plus IR is equal to 0. By definition, we know that IC is equal to C into dV by dt plus IR is equal to V by R, which is equal to 0. So V is the first order value, so we will bring the voltage values to the one side and rest of the values to the another side of this equation. So for that we will multiply the above equation by dt by CV, multiply both sides, so the equation will become C into dV by dt into dt by CV plus V by R into dt by CV is equal to 0. On simplifying this equation, we will get dV by V is equal to, when we the remaining term in this equation is dt by RC. When we are transferring to the right hand side of this equation, the equation will become negative dt by RC. Now we are interested about the voltage value, so we will do the integration on both the sides. So when we do the integration, the integral of dV by V will be natural logarithm of V is equal to, in this integration 1 minus 1 by RC is constant, and when we do the integration, the value of integration of dt will be t plus, for simplification purpose we will consider the integral constant, that is natural logarithm of a. Now we will transfer the natural logarithm of a term to the left hand side of this equation, so the equation will become natural logarithm of v minus natural logarithm of a is equal to negative t by RC. On further simplification, we know that log of m minus log of n, we can write log of m by n, so we will apply here log of v by a is equal to negative t by RC. We know that e to natural logarithm of x is equal to y, and we can rewrite this equation into e to the power of y is equal to x. So in this equation we will take that v by a term is x and minus t by RC term is y. We will apply this form, so e to the power of y, e to the power of y is negative t by RC, which is equal to x is equal to v by a, and we have entered into the time domain form, so we can write v of t. On further simplification, the equation will become v of t is equal to a into e to the power of negative t by RC. Fine. This is the natural response equation for the source free RC circuit, and from this equation we can come to know that the natural response will be exponentially decaying. Okay, further we will rewrite this equation, v of t is equal to a into e to the power of minus t by RC, and we know that the time constant tau is equal to, we can write RC, and the unit of tau is in seconds. Okay, now when we applying the tau into this above equation, v of t is equal to a into e to the power of minus t by tau. By considering the initial values, by considering initial condition when t is equal to 0, that time v of 0, the above equation v of t is equal to a into e to the power of minus t by tau will become v of 0 is equal to a into e to the power of, when we are applying the value t equal to 0 here, so the value of e to the power of minus t by tau will become e to the power 0, which is equal to a, right? Now because e to the power of 0 value will become 1, and we will apply the value of a, that is initial value v0, to this equation. So the equation will become v of t is equal to, we will apply v0 in place of a, so v0 into e to the power of minus t by tau. Further, what we will do is, whenever when t is equal to time constant, that time the equation will become v of t is equal to v naught into e to the power of minus tau by tau, which is equal to v naught into e to the power of minus 1. As we know that the value of e to the power of minus 1 is equal to, as we know that the value of e to the power of minus 1 is 0.3679 times of this initial voltage, that is v0. So whenever the time is equal to one time constant, that time it is reaching the value, whenever the time constant t is, whenever the time t is equal to one time constant, that time the exponentially dropping voltage will reach to a value of 0.367 times of initial value, or the 36.8% of its initial value. Okay, when next we will plot the graph, when we plotting the graph between v and t, and at time t is equal to 0, the initial voltage v0 is available, and as the time is increasing, the curve is start dropping exponentially it is decaying. So the response at any point will be v naught into e to the power of minus t by tau. Here we will consider that when the time t is equal to one time constant, that time the, when t is equal to one time constant, that is tau, the, the response will be 0.368 times of initial voltage. Next we will tabulate the v of t by v0 is equal to e to the power of minus t by tau for different values of t value. When t is equal to one time constant, that time the v of t by v0 value will be 0.36788, because when we are applying the value of t equal to tau here, then the equation will become e to the power of minus tau by tau will be e to the power of minus 1, and e to the power of minus 1 value is 0.36788. Same manner we can apply all the time constant time values, that is t is equal to up to 5 tau, we will get these values. Then we will plot the graph according to the values, and the graph will be look like this. If we are using the CRO or any other graphing platforms, or we are having in the physical graph, that time we want to approximate the one time constant, that time what we need to do is, we need to draw a tangent when t is equal to 0, and that tangent will approximately intersect the time axis at equal to one time constant. When time is equal to one time constant, that time the value of response will be 0.37. If we want to find out the two time constant, that time we need to draw the tangent at one time constant, and it will approximately intersect the time axis at 2 time constant, and so on. We can draw the graph. Now in this table we can see that the difference between two consecutive time constants is 36.8 percentage of decaying value. So we are calculated between 1 tau to 2 tau, that time 36.8 percentage is decayed, and between 2t to 3t then also 36.8 percentage is decaying continuously for all the consecutive time constant. And one more thing we need to note down here is at approximately 5 time constant, the response is reaching the steady state or the final state, because the response at 5 time constant is reaching to the 1% of its initial value. So initial value in this case V0, so the voltage at initial value will be reaching to the 1% of its initial value. That time we are taking it as the it has reached its final state for the approximation or the practical purposes. Now we will see what is the effect of time constants. For the base reference, we have drawn the graph between the v by v naught to the t at t is equal to at tau is equal to 1, at tau is equal to 1 time constant. Then the response is exponentially decaying. When we are increasing the time constant from tau is equal to 1 to 2, that time the time taken to dropping the value from unity to the 0 is comparatively more than the one time constant. If same, when we are decreasing the time constant to 0.5, or we can say half of the time constant, the response is reaching to zero value very quickly comparing to when tau is equal to 1, that is one time constant. Now in, for example, when tau is equal to RC, for different values of RC, if tau is not varying, if tau is not varying, we can use the same response curve for the experimental or the calculation purposes. Till the time, if tau is not varied, we can use the same curve. If tau is varied for any kind, well, any kind of values of R and C, then we need to redraw the curve and we need to perform the calculations as required. Next, we will prove that the whatever the energy stored in the capacitor initially, the capacitor energy initially is of C V naught square. This is the amount of energy stored by this capacitor initially, and it will be dissipated by the resistor over a time period. At t is equal to infinity, it will completely dissipate the whatever the energy stored by the capacitor in the form of heat. That we will prove in mathematically. So we know that the energy stored in the capacitor, energy stored in the capacitor with initial value, that is 0, is equal to half C V naught square. Okay. Next, what we will do is we will calculate the energy dissipated by the resistor. So the energy dissipated by the resistor over a time period t, we can calculate as integration of power dissipated by the resistor with respect to time. The time limits will be 0 to t. To apply this power value, we need to find out the PR value. So the PR is equal to V into I. So as we know that V is equal to V naught into e to the power of minus t by tau, and I value is equal to V by R. V by R is equal to V naught e to the power of minus t by tau by R. On next step, when we simplifying this equation, V naught into V naught will be V naught square into e to the power of minus t by tau into e to the power of minus t by tau will become e to the power of minus 2t by tau divided by R. Now this is PR. We are going to apply it into this formula, that is energy dissipated by the resistor over a time period t is equal to integration of 0 to t power dissipated by the resistor over a period dt is equal to integration of v naught square, that is pr value we are going to apply. Pr is v naught square into e to the power of minus 2t by tau by r into dt. On further simplification of this equation, we will get the constant term v naught square by r. We can take it out, v naught square by r, as after taken out from the integral, the remaining is e to the power of minus 2t by tau. We know one formula, that integration of e to the power of ax will be 1 by a into e to the power of ax. So we will apply the same formula to this point, to this equation. So the equation is e to the power of a will be minus 2 by tau and x will be t. So when we are applying that, the a value will be minus 2 by tau and remaining is e to the power of ax. E to the power of ax will be this term. We will write it here as it is, e to the power of minus 2t by tau with the limits 0 to t. Fine. Now when we applying the limits into this equation, this constant we can taken out from this bracket. So when we taken out, we can write negative v naught square into tau by 2r into, when we apply the value of t in place of t, so the equation will be same, e to the power of minus 2t by tau, minus, when we applying the 0 in place of t, then e to the power of 0 will become, and we know that e to the power of 0 is equal to 1, so we can write 1. Next we know that in this equation, negative v naught square tau by 2r in place, where we know that tau is equal to rc, and we will apply it here. So the equation will become negative v naught square tau value will be rc by 2r into, the remaining equation is e to the power of minus 2t by tau minus 1. So we will write e to the power of minus 2t by tau minus 1. So on further simplification, the equation will be this r will be get cancelled out, and the remaining term minus v naught square by v naught square c by 2, when we multiplying with the internal terms, the equation will become 1 by 2 c v naught square into, the this one will become this side, that is 1 minus e to the power of minus 2t by tau. This is the amount of energy dissipated by the resistor at time t. Now we need to calculate the amount of energy dissipated by the resistor at time t is equal to infinity. We are going to apply the infinity value in place of t in the above equation. So when we are applying, the equation will become power dissipated by the resistor, or the energy dissipated by the resistor at time t is equal to infinity. The equation will become of c v naught square into 1 minus e to the power of minus 2 times of infinity by tau. As we know that e to the power of infinity is equal to 0, so we can rewrite this above equation of c v naught square into 1 minus 0 will be 1. So this is the final value, that is energy dissipated by the resistor at time t is equal to infinity, and which is exactly equal to the initial available energy in the capacitor. I hope we have proved that the whatever the energy has been stored by this capacitor initially has been completely dissipated by the resistor over a time period of infinity. If you have any doubt, kindly write it on the comment box. I will reply. If you have not subscribed my channel, kindly subscribe it. Thank you so much.